Good? Okay, now, still, I mean, I don't think it's obvious from what I've done why I've done it, right? It's just watch what's going to happen. Why would I have looked at this to begin with? It's only because I realized that I derived that formula before and I need these paths to be in opposite directions, and I want to try and get to Green's theorem. But this may turn out to be a disaster. So I'm going to leave this right here on the board. This equals that. Can we do some partials real quick? What is the partial of q with respect to x? What is partial of q with respect to x? You have to do a quotient rule, don't you? So I'm going to do that right here. Partial of q with respect to x is equal to derivative of the top times the bottom minus the derivative of the bottom. X times the top all over x squared plus y squared. Are y'all all right with this? Seems like I lost y'all there. Right? This? Oh yeah, squared. Okay. What does this thing turn out to be up here? You have x squared plus y squared minus 2x squared is what? Y squared minus x squared? You agree? Okay, that's what this is. Minus, what's the partial of p with respect to x? With respect to y? Partial of p with respect to y. I'll do that here. So derivative of the top, -1 times the bottom, x squared plus y squared, minus derivative of the bottom with respect to y, 2y times the top, -y over the bottom squared. And what does that top one turn into? Y squared minus x squared again. So these are the same. And I'm subtracting them. I'm supposed to take this one, subtract this one. So this is what? 0. And the double integral of 0 is 0. Okay. Now this is pretty awesome, because this means that this plus this is 0, right? Holy shit. That means that this plus this is 0, which means that these are the same. I mean, sorry, they're opposite in sign. Sorry. You can just move this one over, right? So I'll do it. The line integral over c of f dot dr is equal to the negative of this, right? Yes? But taking the negative of this is the same as reversing the direction. Yes? So why don't I erase that negative and make that that? Yeah? So what is this telling me? If I want to know this line integral over some arbitrary c, which I never told you what it was, it's the same as the 1 over c1. But that was just a little circle. Now, it only works for this particular vector field. This is not a general conclusion that we're drawing. It's for this particular vector field we're able to do this. And so I think we might be able to do that pretty easily. Let's see if we can, right? Let's see if we can actually do this one. Yes? Why is it only working with this one? Because that's 0. If those partials had not turned out to kill each other off, this wouldn't help us at all. Which is why when they tell you in a problem like this to show this is true, most likely when you go to Green's theorem, you're going to get zeros, or you're going to get 0 to come out. Okay, so I am trying to find, right, this whole problem of trying to show you that this line integral over an arbitrary curve is equal to 2 pi has reduced down to me showing you that over an arbitrary circle of radius a, the answer is 2 pi. So I just need to know this. What is the line integral over C1 of f dot dr? So how would you like to do this? You have options. You want to define C1 as a curve? So let's draw C1. To draw C1, I use a vector function, right? What? What's the radius of that circle? A. So A cosine t, A sine t. That should draw me the curve. T, of course, is bounded between 0 and 2 pi. So that'll draw me that circle, radius A. Now, I think what you're doing, from what I'm hearing, is that you're going to go in here and go 0 to 2 pi. You're going to take the vector field, you're going to plug in r of t, and then you're going to dot that with the derivative of r of t, or of r, and then dt. I believe that's the formula that you're using here. Okay. So we need the derivative. The derivative of r is what? Negative a sine t, a cosine t. You with me? And we get to plug that in, right? We get to plug the r into the vector field, and we need to plug the r prime into this. So here I go. It doesn't look nice, does it? Doesn't look nice, but it's going to clean up pretty good. Equals integral from 0 to 2 pi. And then the vector field with negative y. What's negative y? Negative a sine t. Over, what's x squared plus y squared? If you take these two, square them, and add them together, you'll get a squared after you use Pythagorean identity. So you're just going to get that over a squared. And then there's no square root, right? We're good? Oh, yeah, OK, you canceled already. Yes, I'll do that in a second. Now the x over x. So a cosine t over a squared again. And then I'm going to dot that. Vectors. My angle bracket there is wanting to be something else. OK, and I dot that with the derivative, which is negative a sine t, and then a cosine t, and then dt. And I think we're going to get a really nice result here. When I do this one and this one together, negative a times negative a is a squared sine squared t over a squared, which is just sine squared t. And this is a dot product now, right? So I'm no longer going to have a vector. So I have sine squared t plus, and then same thing happens here, right? A squared cosine squared t over a squared again, doing this one times this one. And the a squareds cancel. You're just with cosine squared t dt. But that's just integral 0 to 2 pi of 1 dt, which is t evaluated 0 to 2 pi, which is 2 pi. So this is a really good example of how something like Green's theorem, although it's nice and we've seen it's useful, if you use it the right way, you can take a problem that seems impossible to do and do it, right? Now, a lot of times in classes that you would take like physics or down the road, a lot of times these results are known. So like for particular vector fields, you know that if you go along any closed loop, you know that the answer is going to be 2 pi. And they more or less provide that to you rather than derive it for you. And so in this class, what we're doing is we're trying to derive where it comes from. Yeah? Okay. All right, moving on. That's the homework. There is not going to be a homework problem like this. I'm not going to give you a test problem like this. This is just to show you kind of the power of what we can do with the Green's theorem. I think that's like the first time I've ever run through that without making any mistakes. There's a lot in that to have to regurgitate. Got that? Okay. The next section is pretty short, it's pretty clean, and it's very visual, all right? I try and make it visual because I think these are two of the coolest things that we can see in this class. It's this idea of curl and divergence. So we know that we have these things called vector fields, right? And if you look at a two-dimensional vector field, that basically says like a flat sheet of paper, at every point there's a vector that points in some direction. And in three-dimensional space, the same thing. So before I talk about these two things called curl and divergence, I wanted to just mention, just look at something visually. I was going to try and give you, bring in an example to show you, hands-on thing. But let's just imagine that we're looking from the top down, and we have this pivot point, and we have this piece of wood, all right, like this, all right? And let's not look at like gravity is down or anything. Let's just say there's no gravity. In fact, we're looking at it from the top, so gravity wouldn't matter. But if I push on this with a force here and a force here at the same distance from the pivot point, and I push with the same amount of force, what's going to happen? No, this is a pivot point, and it's locked in place. Okay, that doesn't move. Well, let me do this. What happens if I just do that? Start spinning, right? It would start spinning this way, yes? Or if we want to look at this almost like a paddle wheel, and you turn on a fan over here and you start blowing, and this will start spinning, won't it? But if I put a fan over here and start pushing with the same amount of force that direction, it's going to be stuck, right? It's not going to move. Okay, and if I do something like this, where I push with a lot of force right there, but then I put, a little bit of force over here, that still might bounce out and it still may not move, right? Exactly, like torque. So the idea here is that all I want you to see is that this picture, I'm about to show it to you in an animation, but the idea is that we have forces pushing on this paddle wheel. All right? And we just need a basic understanding of what happens. So let's talk about curl. The first thing is to understand that we are defining in this section two operations on vector fields. So if someone hands you a vector field, we have these two things called curl and divergence. Curl, when we take the curl of a vector field, okay, when we do that, the answer is a vector. When we calculate what's called the divergence of the vector field, we're going to get a number, a scalar. And what they mean is what I'm going to try and show you. All right? And then I'll show you how to compute them. Or you know what? I'm going to show you how to compute them first. Well, what do you want to see? The computation, or you want to know what they are first? Yeah. You want to know what they are? Okay. Curl. I'm going to do the two-dimensional curl first. Okay, so let's say we have this vector field here, right? This is our vector field. So you can tell that, in the middle, as we move away, right, as we move to the left or to the right, those force vectors get stronger. But they're all pointing in this direction, right? So right now, do you see that my paddle wheel is not moving? That's because the force on each side of the paddle wheel is equal. So what I want you to do is imagine that we're actually looking at a point. We're looking at a single point, and imagining these little, like infinitesimally small paddle wheels, and we just kind of stick them out and we see what happens. If we stick them out and nothing happens, the curl is 0. Curl meaning like twisting, all right, turning. So I don't want to twist. What's going to happen if I slide my point to the right? What's going to happen? I should start spinning which way? Clockwise? Let me try. Okay, you see that? Clockwise rotation. And I'm having the computer calculate the curl for us, which I haven't shown you how to do. Notice that our curl is negative. Yes? Clockwise, negative rotation. Then what would happen if I go to the other side? Should be counterclockwise, right? And my curl is 1.8. Now, watch what happens if I move this further to the left. What do you think is going to happen? Things can start spinning faster. So same direction? Same speed? Let's see. Look, 3.08. The curl got bigger, right? And it's positive, so I have counterclockwise rotation, bigger number, faster spin. So I like to kind of think of this as almost like, think of, if you can, a flat river, okay? This like sheet of water flowing. And let's say it's, how deep is the water? It's only the depth of like one water molecule or something, all right? And so this water molecule is right here. All these other molecules of water are moving down the river with it. So if this little water molecule is going down the river, right, and he kind of sticks his arm out, the guys on the right side hit him, right? The left guys hit him, but not as fast, so he starts spinning as he's going down the river. And so he has this twist to him. And does that make sense? Okay, and so that's the curl of the point. Okay?
That was a nice spin.
You like that? Okay. And then what if I move him up? What if I move him up? Nothing should happen, right? Yeah, the curl's exactly the same, 3.08. Initial settings. Go back to the beginning. All right. Now, what if I change the vector field? So that was this. By the way, this was the vector field. I have it where you can change them. Let's do a more interesting one. There we go. So if I start moving, right now I have 0 curl. If I move this way, I'm getting positive curl. If I move up, negative curl. If I move up, changes a little bit. Did y'all notice that the wheel does spin faster when it gets bigger? You don't understand what it took to make it do that. Oh, did I stop there? I had almost 0 curl there. Look at that. Right up there, I'm getting almost 0 curl. It's turning. I don't know if you can see it turning. I'm going to draw a line right there. Y'all do see it turning? It's very slow, right? Very slow. All right. Understand geometrically the idea of curl. Okay. This is stuff you would use in like fluid dynamics, right? You want to know how your fluid's behaving. Is everything chaotic and spinning around, or is everything just kind of chill, sitting in one place, not wanting to twist? All right, I'm going to pause this because sometimes I bring my computer to its knees. 3-dimensionally. Oh, you know what? Go back to this. I told you that the curl was a vector, right? Okay, right now you can't tell it's a vector. And this right here is actually the magnitude of the curl. I should have told you that. This is the magnitude of the curl. The curl is actually a vector, and the vectors is coming straight out at you. In 2-dimensional, your curl vector is always coming right out at the board. All right? The length of that curl vector is going to be a measurement of whether or not, or how fast it's turning. If it goes into the board, the rotation changes the other way. All right? But in 3-dimensional space, all right, so you see this little thing up there in 3-dimensional space? What that is a point. All right? The red line segment there is the direction of the curl, all right? And that yellow disc is the paddle wheel. So I'm not going to show you the vector, well, I can show you the vector field. There it is.